Okay, let's get started. Yeah, thank you for coming to attend our IC colloquium in this cold day. Today, we're very happy to have Jinwen Yang come from University of Chicago to give us a seminar. And Jinwen is a Ph.D. Candidate in the Department of Statistics at University of Chicago. But his research is on optimization algorithm design, particularly on how to tailoring the linear programming or other optimization algorithms to modern hardware like GPU. And Jinwen has published several papers in mathematical programming and operations research. Yeah, let's welcome Jinwen to give us the talk.
Thank you. Yeah. Hello, everyone. Thank you, Shi, for the introduction, and thank you all for being here. Today, I'd like to share with you some of my recent work on accelerating linear programming using GPUs and how these ideas can be extended to broader classes of math programs. Please let me first summarize my research theme. The high-level research question that drives my work is to figure out if we can use GPUs to speed up and scale up math programming. You know, GPUs are powerful and now widely available. And while these math programs have traditionally been solved using algorithms designed and optimized for CPUs. And when we have a GPU, a new hardware, we would like to ask what kind of optimization algorithms map well on GPU. This leads to the development of new first-order methods and their associated theoretical analysis that both explain the behavior or drive the design of more effective algorithms. And it's really cool to have these algorithms running on a real GPU machine. I co-developed a series of GPU-native solvers for different kinds of math programs. And these computational tools are open source, and we are trying our best to make them more accessible and easy to use. Well, large-scale math programs have found their applications in many different domains. And I'm very happy to realize that our software on GPU help tackle large-scale math programs in production. Okay. So if we look at how large-scale computation evolved over the last 10 years, there's a sharp contrast between machine learning and math programming. On the machine learning side, the infrastructure has grown quite fast. Accelerators like GPUs and other AI chips are now standard computing platforms. First-order methods, such as gradient descent and its many variants, are widely used for training. They may provide less precise solution, but they can handle massive problems. And now, we also have these highly optimized GPU-native framework like PyTorch and JAX to facilitate large-scale computation. As a result, training models with hundreds of billions of parameters are no longer surprising. Now compare this with math programming. For hardware, most software are still optimized for CPU execution. For algorithm, we have simplex and interior point method. They are mature and powerful for moderate-sized problem, and modern optimization suites are engineering models to make this happen. However, some users report that solving a large LP with more than 10 million decision variables can take many hours, even on a high-end server. So there's kind of mismatch on the problem size that can be handled, which brings up the key question of this talk. Can we use GPUs and first-order method to speed up and scale up math programming? First, what is GPU? GPU stands for Graphics Processing Unit. As suggested by the name, they were historically designed to accelerate computer graphics and image processing. Over the past decade, GPU have found many applications beyond graphics. One notable example is the development of AI. As illustrated here, we see sustained growth in the computational capability across multiple GPU generations, with a particularly rapid acceleration in the recent years. To understand why GPU might be used for math programming, it would be helpful to take a quick look under the hood and compare the architecture difference between GPU and CPU. A GPU dedicates most of its silicon area to compute cores. These cores are simple, but there are thousands of them. The control unit is relatively lightweight because GPUs are designed to execute the same instruction across many data elements. A CPU, on the other hand, has far fewer cores. Each core is much more sophisticated and with a substantial control unit to support complex branching. As a result, GPUs are better at parallel massive workloads, while CPU is better at serial control-heavy tasks. GPU also trade off memory. It provides less memory capacity in total, but offers higher memory bandwidth. In other words, GPU memory is more constrained, while its read and write operations are faster. And we'll see this kind of architecture differences largely determine which numerical operations GPU prefers. Here I highlight two linear algebra operations used in large-scale math programming. The first one is to solve the linear system via the sparse Cholesky factorization, which is the computational bottleneck in interpolate method. Here, we have a sparse matrix A, and we want to decompose it into the triangular factor L. In general, it's very challenging and highly non-trivial to parallelize effectively on GPU. The computation has strong sequential dependencies which limit parallelism. What's more, even though the original matrix A is sparse, the triangular factor L can become significantly denser. This increases both the memory usage and the computational cost. The other operation is the sparse matrix vector multiplication, or SPMV. Here we have a sparse matrix A and a vector X. We want to multiply them together and have a new vector Y. It is the dominant computational kernel in first-order method. And we'll see this operation maps naturally to the GPU architecture. So why is SPMV a good fit for GPU? First, for SPMV, each row computes an independent inner product. And this inner product ideally involves only a small amount of non-zeros. This maps perfectly on GPU. I mean, we have a lot of simple independent tasks in parallel. And SPMV is also memory efficient. Beyond storing the matrix A itself, we only need a few extra vectors. No additional matrix storage is required. To be more concrete, let's compare the performance on GPU and CPU. Here, each blue point represents an instance. The x-axis is the number of non-zero in the matrix, and the y-axis is the speed up of GPU over CPU. Points above the dashed horizontal line means GPUs are faster. On the left is sparse matrix vector multiplication. What we can see is a clear and consistent pattern. The speed up is quite remarkable and increases as problem gets larger. On the right is the sparse Cholesky factorization. Here, the picture is much more heterogeneous. Some instances benefit from GPU acceleration, while many shows little improvement at all. Unlike SPMV, the speed up does not scale cleanly with the problem size. Instead, they depend heavily on the matrix structure and its sparsity pattern. This table also compares the memory usage on the same set of instances. The original instance takes around 5 megabytes memory on average. For SPMV, the memory footprint is very small. And for sparse factorization, it requires substantially more memory and consumes hundreds of megabytes, even though the original instance is modest in size. This is especially important on GPU because the GPU memory is more constrained and expensive than CPU memory. Putting these pieces together, GPUs provide greater advantage for SPMV than for sparse factorization, not only in terms of the performance gain, but also in terms of memory efficiency. In this sense, first-order methods are natural candidates to consider. By definition, they are optimization algorithms that rely only on the gradient information. Think about the gradient descent and its many variants. From computational perspective, many first-order methods require only the sparse matrix vector multiplication and entirely avoid matrix factorization. As we already know, the GPU speedup for SPMV are large and consistent and scale well with the problem size. There are several other bonuses of first-order method. For example, the majority of the computational time is spent on SPMV, which means we can benefit directly from GPU acceleration. At the same time, the memory overhead is very low, which fitting well with the GPU memory constraint. In the remainder of the talk, I'll first focus on the GPU-based first-order methods for linear programming. I will introduce our choice of base algorithm and show you the empirical performance of CoPWX, our GPU-based LP solver. Then I will discuss the theoretical insight, provable acceleration, and a refined characterization of PDAG dynamics. And beyond LP, I will briefly touch on the convex quadratic programming and semi-definite programming. All right, here we go. Consider a standard LP in primal form. We want to minimize the linear objective subject to linear constraint. In terms of first-order methods, probably the most natural one is the projected gradient descent. We take the gradient step on the objective with step size eta and project back onto the feasible region. While the gradient evaluation is pretty straightforward, it's just the objective vector C. The projection can be computationally very expensive. It essentially requires projection onto the intersection of a linear subspace AX equal to B and the non-negative ortho. So how to avoid this expensive projection? Well, instead of enforcing the linear constraint AX equal to B, here we introduce the dual variable Y and dualize this linear constraint. So this leads to the min-max problem, where the objective is the Lagrangian. From this viewpoint, solving the original LP is equivalent to find a saddle point of this min-max problem. Given the primal dual formulation, the most direct method is still gradient method, which is also known as gradient descent, or GDA. In each iteration, we take the gradient descent step on the primal variable and do the projection, and then we do the gradient ascent step on the dual variable Y. From computational perspective, it requires a projection onto non-negative ortho. It is essentially coordinate-wise projection, and therefore easy to compute. In each iteration, we require two matrix vector multiplication with matrix A transpose and A, which we already know that GPU handles pretty well. Despite its simplicity, unfortunately, GDA does not converge generally on min-max problem. Consider this simple bilinear example. It has a unique saddle point at the origin. From the red curve, we can see the iterates of GDA spiral further away from the saddle point. So GDA actually diverges on this example. One classical method to solve min-max problem is called the proximal point method, or PPM. Compared to GDA, the difference is subtle but important. In the primal update, instead of relying on the current dual variable yk, we need the next dual variable yk plus 1. And in the dual update, we need the next primal variable xk plus 1. This kind of coupling makes PPM convergent and stable. But the cost is that now the updates are implicit and require solving coupled equations, which is often too expensive to be used directly on large-scale problems. Let's go back to the simple example, but focus on the PPM. From the green curve, we can see the iterates spiral inward to the saddle point. So PPM converges on this example. So can we combine the simplicity of GDA with the stability of PPM? This brings us to the primordial hybrid gradient, or PDAG method, also known as Shambo-Pock method. At first glance, it's pretty similar to GDA. The primal update, take the gradient step, and do the projection. And the key difference comes from the dual update. Instead of using the current primal variable xk, we use the extrapolated point 2xk plus 1 minus xk. This extrapolation makes PPM stable, makes PDAG mimic the PPM dynamic. And from computational perspective, PDAG retains the simplicity of GDA. It requires simple projection onto non-negative ortho and 2 matrix vector multiplications. Finally, let's see how PDAG behave on the example. From the blue trajectory, PDAG also spiral inward to the saddle point, much like PPM, but now with explicit update. So in other words, PDAG inherits the stability of PPM while retaining the computational advantage of GDA. A quick recap. Why are we considering first-order method for LP? Because its dominant computational bottleneck is SPMV, which is highly parallelizable and scales effectively on GPUs. Why do we solve the primal dual problem? Because we want to avoid any expensive projection and linear system solves. And which method do we use? In this talk, we'll focus on the PDAG method as our base algorithm. Now let's move on to the computation. We use LP instances relaxed from MIB models of the MIB-like benchmark dataset. To better understanding the scaling behavior, these instances are grouped into 3 classes: small, medium, and large, based on the number of non-zeros in their constraint matrix. All experiments are run on the modern hardware. For CPU, we use a high-end AMD CPU launched in 2024. And for GPU, we use an NVIDIA H100 for all GPU solvers. So how strong is vanilla PDAG numerically? This figure shows the success rate of plain PDAG on the benchmark dataset. We report 2 accuracy levels: a moderate tolerance 10 to the minus 4 and a tighter tolerance 10 to the minus 8. Each instance has a 10-minute time limit. As we can see, although the GPU implementation outperformed the CPU version, the success rate is fairly low, especially for the high accuracy setting. So this suggests that PDAG alone is not enough. On top of PDAG, we developed 2 GPU-based LP solvers, cuPDLP and cuPDLPX. cuPDLP is essentially a GPU-friendly variant of the CPU-based PDLP. In this talk, I will focus on the cuPDLPX, a more recent and more robust LP solver. It uses a new algorithm called restarted reflected helping PDAG, together with some other numerical techniques. Here we show the new LP-specific algorithm and compare the trajectory of vanilla PDAG and the new algorithm. The green curve is the vanilla PDAG. It spirals and converges slowly. The brown curve is the new algorithm. As we can see, it reaches the settle point more directly and much faster. Later, I will discuss the theory behind restart, reflection, and helping. For now, let's focus on the empirical impact. This figure shows what happens once we use the new LP-specific algorithm. As we can see, the vanilla PDAG has fairly low success rate. With cuPDLPX, the success rate jumps dramatically, reaching more than 97% for the moderate tolerance and more than 95% for the high accuracy setting. So it turns out this enhancement works pretty well. Let's compare the GPU-based solvers with Groovy. Here we report 2 accuracies, 10 to the minus 4 on the top and 10 to the minus 8 on the bottom. Each row represents a single solver. The first 3 rows are grouped with primal simplex, dual simplex, and interior point method, followed by co-PDLP and co-PDLP-X. The results are grouped by sizes, and for each class, we report the solve count and average solve time. As we can see, the performance of co-PDLP-X is overall comparable to Groovy, even at high accuracy setting. And co-PDLP-X demonstrates advantages on large LP if we look at the medium and large instances. Compared to GPU solvers, co-PDLP-X has better performance and more robust performance than co-PDLP. We further test large LPs from practical applications. Here, the instance is relaxed from a MIM model of the linear shipping network design problem. The LP has more than 200 million variables, more than 15 million constraints, and around 700 million non-zeros. The instance itself requires around 15 gigabytes memory. Groovy's interior point method runs out of memory, even with 1 terabyte of RAM. Google's PDLP solved the instance on a CPU, but it took more than 2 days. In comparison, co-PDLP-X solved the same instance on a single GPU within around 7 minutes. The next example is the unit commitment. Here, this table compared the co-PDLP with a commercial inter-point solver. And the instances are relaxed from MIM models, and the model size varies due to different spatial aggregations. I mean, this unit commitment used the German energy system as the geographic basis, and different spatial aggregations will give different model size. As the model grows from several millions of non-zeros to hundreds of millions of non-zeros, we consistently see large speed up of co-PDLP. At this largest scale, interior points simply run out of time after 2 days, while co-PDLP solved the instances within around 8 minutes. This line of research has gradually gained broader attention since the release of co-PDLP in 2023. We have been encouraged to see this PDLP-based method being incorporated into several optimization solvers. And more recently, co-PDLP-X has also seen early adoption from companies like NVIDIA and Groovy. At the same time, our GPU solvers are increasingly being used to tackle large-scale optimization problems arising from industrial setting. For example, the energy system management and the data center traffic routing. Beyond standalone solver, co-PDLP-X is also available in the library MPAX, which stands for the mass programming in JAX. JAX is a Python library widely used for large-scale machine learning. And the motivation of MPAX is to make optimization, make easy integration of optimization as building blocks within a modern workflow. It inherits many modern features like the hardware acceleration. The same code can be executed on CPUs, GPUs, or even Google's TPU. Batch solving, we can solve multiple LP instances with the same scale at the same time. And we also support the automatic differentiation and distributed computing. So if you are interested in MPAX, we could discuss more offline. To summarize, the key takeaway is that co-PDLP-X demonstrates advantages in solving large LPs. And the new LP-specific algorithms are very critical for fast and robust convergence in practice. So far, we've discussed the empirical side. Let's now switch gears and turn to the theoretical results. Recall that co-PDLP-X uses the restarted reflected Halpern PDAG for better convergence. Now, I will introduce what they are and how they lead to provable acceleration. We measure the progress using the KKT arrow. Here, we encode the KKT system of the LP using this big matrix K and the vector H. so that this inequality is essentially the KKT system. And then we measure the KKT arrow using this measures how much this inequality is violated. To be specific, the first two blocks are primal feasibility. The third one represents the dual feasibility. And the last one captures the optimality gap. Traditional results of PDAG are mostly slow sublinear rate. And they essentially treat LPs as a special case of general convex concave problems. However, in practice, many LP applications require moderate to high accuracy solution. In that region, sublinear convergence can become a serious bottleneck, and we want linear convergence rates. The issue of the sublinear convergence is that they do not exploit any special structure of LP. If we can take advantage of that kind of structure, we actually have better convergence rate. And the key concept here is the sharpness of the KKT system of LP. Intuitively, we have this KKT arrow. It is piecewise linear. So we can control the distance to optimality by this KKT arrow up to some constant alpha. Here, alpha is called the sharpness constant. With this sharpness condition, we can show that PDAG actually enjoys linear convergence rate. This complexity has quadratic dependence on the condition number norm of A over alpha. So can we further accelerate PDAG? The answer is yes, and to do so, we need some enhancement. The first one is called the Halpin scheme. So what is Halpin PDAG? Suppose we have the initial point Z0. We take the PDAG step, and then we do the weighted average to get Z1. Then we take the PDAG step from Z1, take the weighted average with the initial point Z0, we have Z2. Then we take PDAG step, weighted average, we have Z3. So intuitively, this initial point serves as an anchor point to contract the iterates backward a little bit for better stability. But the initial point can be a really bad guess of the optimal solution. And this is where restart comes in. The idea is simple. We organize the algorithm into epochs. And within each epoch, we run the Halpin PDAG and monitor the fixed point arrow. Once the arrow is decayed by a constant factor, we restart the method, where we use the current iterates as the new starting point and start a new epoch from there. This figure provides some geometric intuition for why Halpin and restart are effective. The green curve is the vanilla PDAG, a spiral towards the saddle point. The blue curve is the Halpin PDAG. As we can see, the Halpin averaging pull the iterates more aggressively, resulting in smaller spirals. And the red curve is the restarted Halpin PDAG. Here, each triangle represents a restart, and we use the current iterates as the initial point for the new epoch. And once the arrow is decayed by a constant factor, we restart the method and recenter the dynamic. As a result, we can see each epoch start closer and closer to the optimal solution, and the spiral contract geometrically. In theory, we can show the linear convergence of restarted Halpin PDAG. And compared to vanilla PDAG, this rate is accelerated in the sense that we only have linear dependence on the condition number instead of the quadratic conditioning of vanilla PDAG. And actually, this rate is optimal, which means we cannot generally improve this rate among first-order method. But we can still push this idea even further with the restarted, reflected Halpin PDAG. So what is reflection? Suppose we have the initial point Z0 and the current iterates is ZT. We take the PDAG step, then we reflect it to double the effective step size. And we run the weighted average from there. So this reflection essentially takes a more aggressive step and gives a factor of 2 improvement in theory. To wrap up, vanilla PDG has sublinear rate. With sharpness, we can show this rate is actually linear with quadratic conditioning. And help and restart fix this, providing optimal linear convergence rate. Adding reflection improve the constant by another factor of 2. And this restarted, reflected, helping PDG is the core of CoPDRPX. We have shown that both vanilla PDG and the restarted, reflected, helping PDG has linear convergence rate. Recall that this alpha is the global sharpness constant. While the use of alpha is standard in theoretical analysis, we found that it could be overly conservative in practice. Here is a characterization of sharpness for linear inequality system. I mean, this is quite involved as we require a minimization over exponentially many submatrices. So as a result, this global sharpness constant can be very small, even when the algorithm converges much faster. So the question is, can we derive a more refined convergence analysis that avoid relying on this overly conservative sharpness constant? This figure shows the typical behavior of PDG. Each panel represents an LP instance. The x-axis is the number of iterations, and the y-axis is the KKT arrow, the progress measure. As we can see, there are 2 stages of convergence. In the first stage, the algorithm converges slowly and often irregular. After a certain point, indicated by this red vertical line, the dynamic changes sharply. Now the convergence looks pretty linear. So what are the driving forces of these 2 stages? And can we derive a refined convergence rate that better reflects this behavior? To build some intuition, let's look at this simple 2-dimensional LP. Here, the gray area is the feasible region, and the north direction is the direction to go. We have 2 parameters, kappa and delta. Kappa controls the conditioning of the constraint matrix, and it is essentially the height of the top vertex. And delta measures the distance between the top vertex to the top horizontal constraint. It controls the closeness to degeneracy. When delta equal to 0, these 3 constraints intersect at the unique optimal solution, and the LP is degenerate. If delta is small but positive, this LP instance is close to degeneracy. We run PDG with different choices of kappa delta. When delta is small, which means the LP instance is close to degeneracy, like this purple and green curve, the first stage is very slow. When kappa is small, which means the LP instance is ill-conditioned, like this red curve, the second linear convergence stage is very slow. Otherwise, like the blue and green curve, the second stage are pretty fast. So these 2 parameters controls different parts of the trajectory. Delta controls how quickly we enter the fast phase, while kappa controls how fast we actually converges once we get there. So what's happening in the 2 stages? As before, the gray area is the feasible region, and the north direction is the direction to go. The red star represents the convergent optimal solution. In the first stage, the algorithm gradually identified the active set, these 2 red lines. And the main driving force is the closeness to degeneracy. Once the active set is identified, the dynamic essentially restrict to this low-dimensional subspaces determined by these red lines, and we can drop all the blue lines. Essentially, we are like solving a reduced homogeneous linear inequality system, and as a result, typically this reduced sharpness is much better than the global sharpness, as we now only rely on the conditioning of one specific submatrix. And better conditioning implies like better like convergence rate. So we can actually make this two-stage behavior more quantitative for general LP. In the first stage, PDAG will identify the active set within a sublinear number of iterations. The complexity has quadratic dependence on the degeneracy parameter delta, reflecting the difficulty to distinguish nearly active sets. After identification, PDAG will have like local linear convergence rate. Here, the complexity depends quadratically on the reduced condition number. And we can also show the restarted Helpen PDAG preserves the two-stage behavior, and the same acceleration extends to both stages. To be more specific, in the first stage, now the complexity has like linear dependence on the degeneracy parameter delta, followed by the linear convergence stage with only like linear dependence on the reduced condition number. Okay. Now we've seen like great potential of first-order method on GPUs for LP. But obviously, LP is just a starting point. And now I'll briefly touch on the convex QP and SDP. So convex quadratic programming, trying to minimize a quadratic function subject to linear constraint. Here, the matrix Q is a positive semi-definite matrix to guarantee the convexity. In terms of the solvers, commercial packages like Groby and Mosaic rely on simplex or interior point method. On the first order side, we have SES and OSQP. Both of them rely on the alternating direction method of multipliers, or ADMM. However, for this first order method, they require at least one matrix factorization. To design a more like effective algorithm on GPU, it would be helpful to look at two extremes of a general convex QP. So here is a general convex QP. On one hand, when this quadratic term vanishes, we have linear programming. As we already know, restart help like accelerating LP solving. On the other hand, we have the unconstrained convex QP, where we do not have any constraints. And in this classical setting, acceleration is well understood and achieved by the momentum. A general convex QP kind of sits in the middle. So this motivates us to leverage both restart and the momentum. Restart to handle the constrained like LP-like structure, and the momentum to exploit quadratic curvature. We illustrate why both like momentum and restart are essential for practical performance. Here are two representative QP instances. The x-axis is the number of iterations, and the y-axis is the KKT error. The vanilla PDAG, the red curve converges slowly and often stall. Adding momentum alone, the yellow curve does speed things up, but the method can stall as well. Adding restart, the green curve improves the convergence, and the best performance comes from the blue curve, adding like both momentum and restart. This like empirical evidence support our earlier design to use both restart and momentum. We evaluate our method on a standard convex QP benchmark suite as OSQP. We generate 63 instances from 7 different problem classes. And they are evenly split into small, medium, and large based on the number of non-zeros. We compare PDQP, our GPU-based QP solver, against other solvers like the SES on both CPU and GPU, OSQP, and Groby's interior point method. As we can see, our method in the first line solves all the instances across the problem sizes. and it's consistently fast even when the problem gets larger. In comparison, all the CPU solvers, as well as the GPU-based SCS, slow down dramatically or even fail to solve part of the largest instances. Let's finish the QP part by the convergence guarantee. Actually, we can show the linear convergence rate of restarted, accelerated PDG. Here, the alpha measures the error growth in the convex QP. For LP, it recovers the sharpness constant of LP. And for the unconstrained convex QP, alpha is essentially the minimum positive singular value of quadratic term, matching the classical results. And this rate kind of interpolates between these two regions. Now let me briefly touch on the semi-definite programming, or SDP. We are trying to minimize the linear functional on the positive semi-definite code subject to some linear constraint. SDP are more challenging than LP and QP, especially for large-scale problems. We are building up a new GPU-based SDP solver, still exploring, but the preliminary results are surprisingly promising to us. We evaluate our method on the SDP relaxation of large max cut. The instance scales from a million variables to tens of millions of variables. Despite this scale, our method solved many SDPs within 5 minutes. We also test the SDP formulation of large matrix completion. The problem scale up to hundreds of thousands of variables and hundreds of millions of constraints. I mean, despite the scale, our solver can achieve 10 to the minus 5 accuracy within 30 seconds. All right, to wrap up, GPU can be effective for large-scale math programming. CoPLP and CoPLPX demonstrate the potential of GPUs for solving large LPs. They essentially provide a new GPU-native option for LP solving. And the underlying methodology can be extended beyond linear programming. Examples include the convex QP and SDP. And the lesson I learned is that to fully exploit GPUs, we may require some rethinking of optimization algorithms. We want our algorithm to be tailored to GPU architecture so that we will have faster iteration speed. We also want our algorithm to be aligned with problem structure so that we will have faster convergence. And a careful GPU-aware implementation enable high GPU utilization and better scalability. Well, with all this evidence, I believe we can use GPUs to speed up and scale up math programming. Looking ahead, I plan to continue developing GPU-tailored method and their associated theoretical understandings, as well as developing corresponding computational tools for broader problem classes, and to connect these advances to the practical applications. And this concludes my talk. Thank you.
Hey, thanks. Great talk. So this is not my area of research, so this might come off kind of weird. So please, other optimization people, don't judge me too harshly for how I'm. Yeah, Jim, I'm looking at you. So it's very impressive, right? In the fact that your algorithms work for large instances is great. But what maybe you could talk a little bit more is it seems that the algorithms you propose use a lot of kind of classical ideas from first order methods. So why has no one come up with these algorithms before? Is it really that it's more about implementing them on GPUs, or where does this position itself in the broader kind of literature on first order methods and what people have thought of before in terms of that?
Yeah, that's a great question. So trying to use first order method to solve LP is not a new idea. I think like some researcher explored this kind of idea in the 60s. But I mean, back then they primarily like look at the kind of projected gradient descent, and they need the projection back onto the feasible region. So, and back then there's no GPU, only CPU. So I mean, yeah. And right now, I would say this kind of work is a consequence between it's a consequence of both the hardware development as well as the theoretical understanding. So right now, like GPUs are powerful, and they are more and more powerful. So this kind of the computational results are like utilize the power of GPUs. And I would say it will be significantly slower if we use this kind of method, probably say like 5 years ago on the GPU. And for the algorithm side, so even though the pieces are existed in the existing literature, but no one like kind of know that this kind of techniques can be utilized on the linear programming. They basically like study the generic, say like minimize fx, f is like convex, and the important point is that we identify the special structure of LP, which is called the sharpness, and then we can show like how to improve the rate and what kind of technique can help improve the rate in what sense, both the like condition number or the constant. So I feel like it's like the consequence of combination of both like hardware technology and the like theoretical understanding. Yeah. Jim.
Thanks for the very interesting talk. I probably have a couple questions, but I'll start with one. So I noticed in the computational experiments that I think you had turned off pre-solve when you compared against like Roby, and I understand why you would do that, so it's kind of an apples-to-apples comparison. But of course, it is well known that pre-solve has a big impact on simplex, at least for sure, maybe until your point. Can you say anything about what you expect in terms of pre-solve for these methods, and if there might be some need for developing specialized pre-solve for these methods?
Yeah, that's a very great question. So actually, I have I have the results like to compare our like GPU solver with the Groovy, with this like a Groovy LP pre-solve enabled. So these instances are like LPs, not something like MIP pre-solve. And okay, so pre-solve is a process we are like trying to say like identify infeasibility and pre-process all these instances for like better convergence for primal simplex, dual simplex, and the interior point method, because we use the Groovy's pre-solve. And we can see the pre-solve significantly improved the solve count and solve time, not only for the Groovy, but also for our GPU-based solvers. And I would say, okay, so these pre-solves are designed for Groovy, designed by Groovy and for Groovy methods. So we can see like significant improvement for Groovy methods. And in this sense, like for moderate tolerance, our GPU solver are still like very competitive to the Groovy method. But for the high accuracy region, I mean, it's a little bit worse. And I feel like it's expected because we don't have a pre-solve designed for first order method. And I believe this is a future direction. Actually, our solver recently has an option of a very lightweight pre-solve. It's like handmade pre-solve. So not as like sophisticated as Groovy's pre-solve, but it does help the convergence of our GPU-based method. And yes, this like what kind of pre-solve will help first order method is a future direction to work.
Okay, thanks. And then maybe I'll just follow up with just a different question, just a clarification on some of the results for the SDP. Mm-hmm. Some of those results had like the number of variables n. Mm-hmm. Just wanted to understand, is that like the number of elements of the matrix, or is it like n by n matrix in the SDP size?
N by n matrix. For the max cut is n by n, right?
Okay.
Yeah.
Okay. Very large scale. Thanks.
Other questions from the audience? So you said you want to extend your method in the future to nonlinear programming and mixed integer programming. So in your mind, what are the main difficulty you need to overcome to
That's a great
extend?
question.
Yeah.
So I feel like for nonlinear programming, I'm not sure what is the right structure to be exploited to accelerate the convergence. I mean, GPU is a powerful hardware. You can achieve fast iteration speed, but I mean, first order method require a lot of iterations to converge. Then we have to use special structure of the problem. But for NLP, say SDP, we are still exploring. We have not figured out what kind of special structure can be exploited to accelerate our first order method. And for mixed integer programming, I would say, okay, so CPU GPU communications are fairly expensive. And for MIP, you will have that kind of branch and bound. Of course, you can substitute the root node relaxation and each subnode by our GPU-based solvers. But by then, you have to frequently communicate between CPU and GPU because the tree is on the CPU. And you cannot migrate this tree onto GPU because it's strong, it needs complex branching. It's not what GPU prefers. But on the CPU, then you incur frequent CPU-GPU communications. So yes, definitely that deserves more research along this line for GPU-based MIP solver.
Okay. Yeah, another question I have is on the implementation side. I notice in your computational comparison, you run your CPU case on AMD CPU. But it's known for AMD CPU is not really optimized for this scientific computing. Intel GPU have a much better low-level library for this computation. Did you notice the difference on Intel CPU and AMD CPU?
Yeah, I mean, if I understand correctly, you are talking about, say, the MKL library for the Intel, right? Yeah, so this kind of CPU is the best CPU we can get access to. And we try really hard to find a good CPU. And we do have a Intel, say, 8000 series, and we tested it's worse than this AMD CPU. So actually, this is the best we can find. And maybe to our surprise, the high-end GPUs are more accessible than high-end CPUs.
Okay.
And probably the reason is that there's huge demand for GPUs. Okay. But there are limited demand for top-end CPU, so it's really hard to find one.
Okay. Any other questions? Okay. On behalf of our department, we show our appreciation.
Thank
There's
you.
a small gift for you.
Thank you.
Yeah. Thank you. Yeah.
Thank you all.
So we'll work